Let's get started. Here we go. Today we're talking about integration by partial fractions. It's the last of our major integration techniques that we're going to be learning. Okay, so this is what we are covering today. A few announcements. There's homework due tonight. Make sure you get it done. And announcement 2, there's new homework assigned in Canvas. Okay, so any questions on these 2 announcements? Hopefully everyone had a wonderful weekend and we're all ready to learn. Okay, so these notes, by the way, are going, I'm not gonna blast through 61 pages. They're gonna take us a couple days. So just so everyone knows. Here we go. So let's start blasting through these. Here we go. So today's goal, the mission, is we want to learn how to integrate functions that look like 1 over x squared times 1 plus x squared. After probably tomorrow, we'll be able to integrate something that looks like that. And after today, we'll be able to integrate something that looks like this. The integral of 3x over x squared minus x. Okay, so this isn't just a simple u substitution, right? If you would want to make u the bottom, u is 2x minus, or sorry, x squared minus 2, but then dx is 2x minus 1, and that doesn't perfectly take care of that 3x up top. So we need to develop a more sophisticated way to handle this type of integral. Okay, so that's what partial fractions is all about. For people who just came in, Jet and Mark, today's about that. All right. So we're going to get into the weeds a little bit of how to integrate something that looks like this. And it's going to seem unrelated to integration for a little bit. But remember, we're connecting it all back to we want to integrate stuff that looks like this. So currently, we could maybe use trig substitution for, but it's going to give us an easier way to do that. Okay. Now, trig substitution is still definitely a necessary method to know. If there's any square roots happening in your integral, then trig substitution should be the first thing that comes to your mind. Okay, if ever you're integrating something that's the square root of a squared minus x squared, or a squared plus x squared, or x squared minus a squared, that should be trig substitution. But when there's no square root, then the method we're going to learn, if we have a product of stuff in the denominator, the method we're about to learn today, is going to be both, in my opinion, easier and more useful, because trig substitution, remember, that sort of restricts what x can be. What we learn today won't put any restrictions on x when we use this method. Okay? So that's an overview of what we're doing, why we're doing it. Always ask, why am I doing this? Why am I here? Okay. So the main motivation is we want to integrate stuff that looks like this. Something, I want to take the integral of 1 over x squared minus 2x. I think a problem like this, almost exactly like this, was on your homework, where you complete the square and then you use trig substitution after u substitution. I'll admit, it's annoying. Today's method is going to be a little easier. So let's say you forget for a moment that you could complete the square and use trig substitution on this. Well, then we're kind of out of luck unless you realize that 1 over x squared minus 2x is the same thing as minus 1 over 2x plus 1 over 2 times x minus 2. How did I know that? Well, that's what today is all about, is figuring out how to make a rational function on the left look like the thing on the right. Well, if you knew that 1 over x squared minus 2x is that thing on the right, well, the thing on the right is a lot easier to integrate, right? Does everybody see that? Because the integral on the right, well, the integral of 1 over x is natural log of x. The integral of 1 over x minus 2, that's just natural log of x minus 2. So it's much easier to integrate the thing on the right than the thing on the left. Okay, so like I said, this integral is equal to, let me put in the frame here, equal to, well, I could break this up into -1/2 times the integral of 1 over x dx plus 1/2 times the integral of 1 over x minus 2 dx. And integrals of sums are a lot nicer to work with than integrals of products. So this is -1/2 times, again, the integral of 1 over x. This is something that's going to come up a lot today. The integral of 1 over x is the natural log of technically the absolute value of x. Plus 1/2. I could use a u substitution on this integral, right? I could do u is equal to x minus 2. So that means du is dx. And I would get the integral just of 1 over u du after I make that substitution. And that integral is the natural log of the absolute value of u. And that would give me, after I plug u back in, that would give me natural log of absolute value of x minus 2. And then don't forget the c. So when you do this with, if you were to complete the square and use a trig substitution, your answer would actually look a little different. They would be the same answer on a specific interval, but this answer is actually what I would call more correct. This is an antiderivative of 1 over x squared minus 2x on the whole real line, except for at 0 and 2. Okay. Whereas if you use trig substitution, you get an antiderivative that's only valid on a smaller set. So this is a more useful method in this case. So that's the motivation, taking something that's hard to integrate, turning it into something that's a little bit easier to integrate. And the way we do that is by what's called a partial fraction decomposition. We're going to find out, how did I take this thing in that previous slide and turn it into this? Okay. And it's going to let us integrate, in theory, any rational function known to man. So let's dive into how is this actually done. Okay, so in general, today we're trying to find a partial fraction decomposition of a rational function. Who doesn't know? Someone tell me what a rational function is. I mean, I have it right here. So it's p of x over q of x, where p and q are polynomials, right? So polynomials in particular, where the degree of p of x is less than the degree of q of x. Does anyone not remember what the degree of a polynomial is? In case anyone is scared to say they don't remember, if I have a polynomial p of x is like x, here's a specific example, x to the 5th plus 4x squared minus x to the 10th. The degree of this polynomial, degree of p of x, is 10. It's the biggest exponent that you see in a polynomial, okay? So we're going to be focusing on rational functions where the degree of the top is smaller than the degree of the bottom. That's actually a very important thing to remember. You're going to get a problem where that's not satisfied and you do a bunch of work and it was worthless because you need to first make sure the degree of the top is smaller than the degree of the bottom. Okay, why do I have that restriction? Well, if you're given a rational function where the degree of the top is bigger than the degree of the bottom, you can just use polynomial long division to rewrite that as some polynomial plus r of x over q of x, and then this rational function does satisfy. The degree of the top is smaller than the degree of the bottom. Okay, so we'll see some problems where the degree of the top is bigger than the degree of the bottom, but then you just do polynomial long division to turn it into a polynomial plus something where we're in a case that we want. Okay, so let's look at that in case anyone forgets polynomial long division. Technically, it's supposed to be taught in pre-cal, but you know, people forget it. So let's look at polynomial long division. I want to take x squared minus 3x plus 1 and divide it by x minus 1. Okay, so the degree of the top here is bigger than or equal to the degree of the bottom. So I'm going to do polynomial long division, x squared minus 3x plus 1. And I'm dividing that by x minus 1. Okay. Who remembers what's the first step in polynomial long division? I want to find something, I want to find something that I can multiply x minus 1 by so I can get this leading term, x squared. So what can I multiply x minus 1 by so that I get an x squared out of it? Just x, exactly. Really x, you're right, x minus anything, but the easiest thing, I just want to focus on the x part right now. So x, and I'm going to put it over the term that has an x, right? So I write that x down, and then I actually do that multiplication. X times x minus 1 is x squared minus x. And then really plus a 0 if you want. And then I'm going to take the difference. Okay. So x squared minus x squared, well, that's 0 because that's how we picked x, right? So that's going to go away. Minus 3x minus a minus x gives me minus 2x, right? Minus 3 minus minus 1 is minus 2. And then 1 minus 0 is plus 1. Okay, almost there. So what can I multiply x minus 1 by to get minus 2x plus 1? Or sorry, to just get a minus 2x. Yeah, exactly. I want the x, sorry, someone was going to say it. I want the x part to be a minus 2. Well, if I multiply x minus 1 by minus 2, I'll get a minus 2x. Okay, so I'll multiply by minus 2. So when I do that, I'm going to get minus 2x. I multiply this by minus 2. So minus 2x plus minus 2 times minus 1 is plus 2. And then I'll take a difference there. Okay, so minus 2x minus minus 2x. Again, because of the way we chose minus 2, that has to be 0. So 0. And then 1 minus 2 is minus 1. Okay, so this is the remainder. In that previous slide, I called that r of x. And so that means this is equal to, well, whatever we get right here, x minus 2 plus the remainder. So plus the remainder, which is just minus 1. But if I had done x squared minus 3x plus 1 divide, or sorry, if I had done like x cubed minus 3x plus 1, my remainder is actually going to have an x in it. Okay, so this is a special case where my remainder is a constant. The numerator is a constant. Okay, so the remainder over what I'm dividing by. Just like when you're doing long division with just integers, right? You write your remainder over the thing that you are dividing by. So that was a refresher on polynomial long division. Did I lose anybody at any point, or are there any questions about anything I did up here?
Wait, is that x minus 1? What you're dividing?
X, oh, thank you, x minus 1. Thank you very much. Divide by what you were dividing by. All right, so that's why we're only dealing with things that look like P over Q, where the degree of P is smaller than the degree of Q. Because if that's not satisfied, I can always rewrite that function as a polynomial plus something where that is satisfied by polynomial long division. Okay, so once we've done that first preliminary step of polynomial long division, if it's necessary, then the next most important thing that you need to do is factor Q. So you're going to be doing a lot of factoring with these types of problems. Okay. So depending on how Q factors, there are really 4 different paths that will go down. 2 of them, it's really 2 paths where we have one special case in each of the 2 paths. Okay. So we're going to start off with the easiest case, because let's start easy and then get hard. Okay. So here we go. Let's say Q of X factors like this into just a bunch of distinct linear factors. So a specific case of this, I'm trying to be as general as possible, but don't let that scare you. I mean, something that looks like this could be like Q of X is that last one, the bottom, let me go back. This technically is like that, right? Q of X factors, it's already factored. It factors as X minus 1, okay? Back here, let me go all the way back. Back here, this is another case like that. This is 1 over, this factors as X times X minus 2, right? This is a case where Q of X, the denominator, factors into 2 distinct linear factors, okay? So this is going to be the easiest case, and it's also going to be a fairly common case, okay? So let's look at what happens in, let's look at what happens in this case, okay? So again, I'm keeping it general, but you could think of, for instance, like X minus 1 times 2X plus 3, something like that, for instance, okay? And then P of X over Q of X, well, that's the same thing as P of X over A1X plus B1 times A2X plus B2 times ANX plus BN all the way up, that product all the way up. Again, if you want to focus on a specific case, if you're focusing on the case at Q of X is X minus 1 times 2X plus 3, I'm just picking those at random, then this is like saying P of X over Q of X is P of X. I'm just writing out Q of X in terms of its factors, okay? That's all I'm saying there. Now, the key step in finding a partial fraction decomposition is to make a guess. I'm going to make a guess that I can write this P of X over all of that jazz as P of X over A1X plus B1 times A2X plus B2 times ANX plus Bn. I want to rewrite this as a capital A1 over A1X plus B1 plus capital A2 over A2X plus B2 and so on, plus all the way up to capital ANX plus BN. Okay. And the reason I'm sort of justified in guessing that P of X over Q of X looks like this is just how we know how to simplify fractions like this, right? if I were to give you something like this and say, simplify this, what would you do? Ignoring the left-hand side for a second. If I gave you a big sum of 1 over x plus 1 plus 1 over x plus 2, how would you simplify that? Exactly. You would find a common denominator and then add everything up. But that's exactly what, if you were to simplify the right-hand side, the common denominator would be this product of functions, right? It would be a1x plus b1 times a2x plus b2, and so on and so on and so on. Okay, so that's why we're justified in making that guess. Okay, and that's the key step in partial fraction decomposition. Really, in every case, that's the key step, is writing the thing on the left as a reasonable thing to guess on the right. It's going to change depending on the factors, but that's really the key step every time. Okay, and again, don't let, most of the time there's only going to be 2 or 3 factors at most. Okay, so don't let the n scare you. Most of the time it's going to be like, it's going to look way nicer than this. Okay,
So how do we get A?
oh, it's such a good question. It's like I planted you in the audience. Let's look at an example to figure out how we get A1s and A2s and A3s. Okay, so let's find a partial fraction decomposition for this rational function. Okay, so step 1, we need to make sure degree of the top is small, strictly smaller than the degree of the bottom, and that's satisfied here, right? The degree of the top is +1, the degree of the bottom is +2. We're good to go. Cool. Step 2, I need to factor the bottom. Okay, so x squared minus 4x plus 5. Who knows what that factors as? Yeah, it's going to be, did I mess this up? I freaking messed this up, didn't I? I messed this up. Hold on, sorry. It should be this should be a -5, right? Yeah. All right. Sorry, everybody. That should be a -5. Now, to be clear, if you can't factor that, we can still handle this with partial fraction decomposition. But that's going to be a later, slightly more difficult case. Okay, but I meant to put something that we can factor, and so this is the thing that we can factor, -5. So that's going to be x -5 x plus 1. There we go. All right, there we go. So x -5, sorry, there we go. X -5 times x plus 1 is how this factors. So I want to rewrite 2x minus 3 over x squared minus 4x minus 5. I want to rewrite this as a, and in the previous slide I used a1 and a2 and a3. Usually there's not going to be 20 factors. I'm just going to use capital A and capital B. I'm just going to use capital A over, well, let me rewrite this really quick. This is 2x minus 3 over x minus 5 times x plus 1. So I'm going to write this as capital A over the first factor, x minus 5, plus capital B over the second factor, x plus 1. All right. And then the big question, how do I find A and B? Well, let's say for a second that, come on, let's say for a second that we didn't know where this came from. Beautiful, come on, delete. I can do this. Square. Style. Fill. There we go. Let's say for a second we didn't know where this came from. I gave you the problem. Simplify a over x minus 5 plus b over x plus 1. What would you do? I would find a common denominator, and clearly the common denominator is x minus 5 times x plus 1, right? So if I didn't know where this came from, I would rewrite this as a over x minus 5 plus b over x plus 1. That's equal to, well, the common denominator, a common denominator, is just the product of their denominators, right? So I could multiply top and bottom of the first term by x plus 1, right? And I would multiply top and bottom of the second term by x minus 5. B times x minus 5 over x minus 5 times x plus 1. Okay. And when I do that, I end up with a times x plus 1 plus b times x minus 5 over x squared minus 4x minus 5. And it seems like I just went around in a circle, right? Like, why did I do that? We broke this down and then we put it back together. But now I'm going to remember where this came from. This came from 2x minus 3 over x squared minus 4x minus 5. Okay, so I want to make sure that this is actually equal to, I want to pick a and b, so that 2x minus 3 over x squared minus 4x minus 5. I want to make sure that that's equal to a times x plus 1 plus b times x minus 5 over x squared minus 4x minus 5, right? And so if those two fractions are equal and their denominators are equal, then what has to be the case? Two fractions that are equal with the same denominator. Yeah, Mark. No, just if two fractions are equal and they have the same denominator, then what has to be true about the numerators? The numerators are equal. If they have the same denominator and the overall fractions are equal, then the numerators have to be the same as well. So that gives me this equation to solve here. 2x, I set the numerator is equal to each other, right? 2x minus 3 is equal to a times x plus 1 plus b times x minus 5. Okay. And now at this point, I'm going to show you we're going to solve this twice. There are two distinct ways you can solve this. And they'll both be useful in different contexts. Okay. First, I'm going to show you in this case of non-repeating linear factors, this is going to be the easiest thing to do, and it's called strategic. There's an R in strategic substitution. Substitution. There we go. Okay. And the idea here is that the top has to be equal for all x, right? Back here, these two rational functions were equal for all x that I can plug in. So that means that the tops have to be equal for all x that you can plug in. And it actually happens to be the case that they have to be equal for every x on the real line. Okay. So who can tell me what would be maybe two convenient x values to plug in to solve for a and b? Because I can plug in for x. This has to be true for every x. Perfect. If I plug in x is equal to -1, then this equality still has to hold. It has to hold for every x. So when I plug in x equals -1, Well, on the left, I'm going to get -2 minus 3. And on the right, I'm going to get, well, when I plug in -1 into that first term there, it goes away. That was the strategic substitution. Plugging in things that will make terms go away on the right-hand side. So I'm going to get 0, a times 0 is 0, plus -1 minus 5, so -6b. Questions? So we know that -5 is equal to -6b, or in other words, b is -5 over -6, which is also 5 over 6. So we got b. The other x that we could plug in is 5. If I plug in x equals 5, that's going to make the term with the b go away and will be very convenient for us, right? So when I plug in x equals 5, well, on the left, I plug in x equals 5, I'm going to get 2 times 5 is 10, minus 3 is 7, equals, and when I plug in 5 on the right, well, I'm going to get 5 plus 1 is 6 times a, and then plus 0, because again, we chose that number 5, x equals 5, strategically to make that part go away. And that tells me that a is equal to 7 over 6. So again, in the case of where Q factors into distinct linear factors, which means there's no factors that look like, for instance, x minus or x plus 1 squared. We're going to cover that case in a second. But if there's no repeating factors, this is the easiest way to solve for the capital A and the capital B and so on and so on. Okay. So that was strategic substitution. Let me underline it in red. Wow. Now, there is another way to solve for these, and it's also going to be important to know. Okay, so the other way to solve for these is called matching coefficients. Okay, and to do this method is exactly what it sounds like. I'm going to match up the coefficients. So on the left, I have 2x minus 3. On the right, if I rewrite that so I have something times x plus a constant, so it's like it is on the left, well, to do that, I would rewrite this as ax. I would distribute the a, so ax plus a. And I would distribute the b plus bx minus 5b. Okay. And then I would rewrite this as I would collect my x's together. So when I collect my x's together, I have an a plus a b times x. And then when I get my constants together, I have plus a minus 5b. And then I match coefficients, okay? So I match the coefficient on the x. Again, these have to be equal to each other for every x. So that means that the coefficient on the x has to be the same thing as the coefficient over here on the x. So that means a plus b has to be equal to 2. And that also means the constant has to be the same. So that means a minus 5b is equal to minus 3. And I think a few people have taken linear in here, right? This type of system should look very familiar to you if you've taken linear. If not, there are 2 ways to solve this. You could solve one equation for one variable, plug it into the second equation, get an answer for the second equation, and or sorry, the second variable, and then plug it back in to the first equation. Or something that I like to do in a case like this, a plus b equals 2, a minus 5b equals minus 3. I like to take a difference of these two equations. And when I do that, I'm going to get a minus a is 0. B minus 5b, well, that's 6b is equal to 2 minus 3. So 6b is equal to 5, which tells me that b is equal to 5 over 6. Just like we knew already it had to be by using strategic substitution. And then once you have that, you can plug that into the first equation, and you get, again, we already know this, a has to be 7 over 6. So that tells me then, coming back here, that tells me that 2x, actually, let me come all the way back here. That a, we know, was 7 over 6. So a was 7 over 6. And b, I can just replace that now with 5 over 6. Okay. Which you can I prefer to rewrite this with the 7 over 6 out in front. So like 7 over 6 times 1 over x minus 5 plus 5 over 6 times 1 over x plus 1. And we have found the partial fraction decomposition. And you might say, that wasn't any easier than trig substitution. I promise, the more you do these, especially in this case of repeated or non-repeating linear factors, the quicker you'll get at solving that system using strategic substitution or by matching coefficients. Okay. But let's remind ourselves why we did this. We want to integrate 2x minus 3 divided by x squared minus 4x minus 5. Okay, replace that plus with a minus. Well, the way we're going to do this is this integral 2x minus 3 over x squared minus 4x minus 5 with respect to x is equal to the integral, I'm going to paste what we found, is equal to this. That's the partial fraction decomposition that we just found of this rational function. Okay. So let's take a second. Once everyone has that written down, everybody take a second and do the rest of this integration on your own. We'll see if we arrive at the same answers. All right. All right, so, I mean, the reason we find this partial fraction decomposition is so that we can break this up into a sum of integrals, right? So what did we get for, someone tell me what you got for the first integral. Technically, it's a u substitution. U is x minus 5, so du is dx. So then I'll get the integral of 1 over u du. That gives me natural log of u, and you'll end up with natural log of x minus 5, absolute value of x minus 5. Okay, and you do the same thing for the second integral, and voila, there we are. Okay. Any questions on this? Okay. So that took that integral that would have been difficult to do because again, it's not quite, it's heartbreakingly close to a u substitution problem, right? If this was 2x minus 4 up here, then we would be on easy street. I don't know what that term means, but then we could just use u is x squared minus 4x minus 5, du would be 2x minus 4, we would be golden. But we can't do that. U substitution wouldn't quite work for us. Okay. Questions? All right, so that last example again showed the two main ways, not the main, like the only ways that we're going to find the constants in our partial fraction decomposition. And that's equating coefficients or matching coefficients and strategic substitution. Okay. Like I said, both methods will always work, but there are going to be times where strategic substitution is the better choice, better meaning less work. And there will be times where equating coefficients, I know it doesn't seem like it, but there will be times where equating coefficients is going to be less work than strategic substitution. So it's good to know both ways. All right, so let's step back for a second. That was one of, I said there were 4 cases. Really, there's 2 cases, and each one has a special subcase. Okay, but let's look at an example to figure out what we're going to do for the next case. So how would you calculate, how would you calculate 1 over x minus 1 plus 1 over x minus 1 squared plus 1 over x? If I asked you to simplify that, what would you do? Yeah, exactly. That's the answer every time this class and next class is get a common denominator, right? And the common denominator now, when before I just said multiply all of the denominators together, here we can make a slightly smarter choice, right? Here we can make a slightly smarter choice for the common denominator. And what would that common denominator be? Exactly, x minus 1 squared times x. If I were to multiply everything together, it would look like maybe x minus 1 cubed over or times x. And that is a common denominator, but it's not the most efficient choice for a common denominator. Okay. So I would get this common denominator of x minus 1 squared times x. Well, to do that, I would multiply the first term by x times x minus 1. I would multiply the second term by x, top and bottom, and I would multiply the last term by x minus 1 squared, top and bottom. Okay. Equals. So I would get a common denominator. And then if I simplify, this is x squared minus x plus an x, and then plus x squared minus 2x plus 1 over all that jazz. Okay. So x minus x cancels, and I'll be left with 2x squared minus 2x plus a 1 over x minus 1 squared times x. Okay. So if we saw this in the wild, if I asked you to find a partial diffraction composition of this, well, then this came from this, right? So apparently, if I have a repeated linear factor, I need to not only have that x minus 1 squared in the decomposition, I also need this 1 over x minus 1 as well. Okay. So, oh wow, I forgot to change that slide. So when we're writing this out, it's not sufficient to just take a guess that the partial fraction decomposition looks like this. Like maybe it's just, if I'm trying to find a decomposition of this thing, maybe I just need a1 over x minus 1 plus a2 over x. Or maybe I just need a1 over x minus 1 squared plus a2 over x. No. This came from this thing. So I have to have both of these terms present in my partial fraction decomposition. Okay, so I really thought I'd change this, my bad, guys. I need to have, if I'm looking at the partial fraction decomposition of 2x squared minus 2x plus 1 over x minus 1 squared times x, my partial fraction decomposition needs to have both something over x minus 1 and something else over x minus 1 squared and something else just over x. Okay? This is how we deal with repeated linear factors. And in general, this is what's going to happen. If you have a repeated linear factor that occurs, let's say we had something that was like 1 over, 1 is bad. Let's say we had x over x minus 3 cubed. I wanted to write that as a partial fraction decomposition. Well, you have to do this for every time that linear factor repeats. So I would write this as a over x minus 3 plus b over x minus 3 squared plus c over x minus 3 cubed. Okay. And so on and so on. You have to have one term for every integer between 1 and the number of times it repeats. So here's the general rule. If you have repeated linear factors, if q of x factors into something that has an ax plus b to the n, then the partial fraction decomposition should contain terms that look like this. A1 over x, ax plus b plus a2 over ax plus b squared, and so on and so on and so on and so on, all the way up to an over ax plus b to the n. But then you can still use the same methods to solve for those constants that we used before. Either strategic substitution, which takes a little more work in this case, or equating coefficients, which is actually, equating coefficients is always the exact same amount of work as that first example, okay? So tomorrow we're going to actually write this example out, but for now, let's look at how we would do this. Find the partial fraction decomposition of the rational function 3x squared minus 3x minus 2 over x squared minus 1 times x minus 1 squared. So is the bottom, is q completely factored? It's not. Because, I mean, that's a repeated linear factor. There's nothing I can do about that. But what does x squared minus 1 factor as? Good. So this really I can rewrite as x minus 1, x plus 1 times x minus 1 squared. And so this becomes 3x squared minus 3x minus 2 over x plus 1 times x minus 1 cubed. Okay. And so tomorrow we're going to solve for these coefficients, but tomorrow we're going to write this as a over x plus 1 plus b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. And we'll pick up from there tomorrow. So thank you all for being here. You actually have enough to get started on the homework. The homework is almost entirely partial fractions, okay? So if you want, you can get started on the homework and come to me in office hours if you have any questions. Office hours today from 10 to 12. So have a great day, everybody. I'll see everybody tomorrow, and we'll pick up from here.
Thank you.
Thank you.
Thank you.